So in abstract algebra, we are discussing about groups and subgroups based on the Lagrange theorem and theorems based on like subgroups. We are solving some problems. One among the problem is if G is a finite group and H and K are subgroups of G such that order of H is a greater than order of G, root of order of G, and the order of K is greater than root of order of G, then order of H intersection K can can be 1. This is the yes, this is the question. Solution. We know that if H and K are subgroups of G, then order of HK equal to order of H into order of K divided by order of H intersection K. Here, order of H is greater than root of order of G, so we can able to substitute this order of G. Instead of order of K, we can able to substitute order of G divided by order of H intersection K. Right? Okay. So both terms are same. So order of G divided by order of H intersection K. Right? So here, so we are getting order of HK, right? Order of HK is, so here HK is a subgroup of G. Therefore, order of HK is less than or equal to order of G. So just from this, we can able to rewrite like this. Order of G divided by order of H intersection K is less than order of HK, which is less than or equal to order of G. Just combine this, you will get order of H intersection K equal to 1. This is the answer. Right? Very simple question. Question number 2. If G is a finite group of order n, if G is a finite group of order n and A belongs to G, such that A power m equal to E, A power m equal to E, and m comma n are relatively prime. Relatively prime, then A is equal to E, which is true or false. If order of G equal to n, A belongs to G such that A power m equal to E, then m and n are relatively prime, then a equal to e. Use the same procedure, you get a work done. So yeah, workout. This is for your practice alone. Next, like true or false questions have been asked in TAF, Tata Institute of Fundamental Research problems. Again, one more TAFR problem, TAFR 2010. If order of G equal to 8, then there exists A belongs to G such that order of A equal to 2. Now you have to say which is true or false. If order of G equal to 8, then there exists A belongs to G such that order of A equal to 2. So we need to verify whether it is a true or false. So let's see here. This is 8. Then there exist elements x such that x is not equal to identity element. Right? So let that x belongs to a group G such that x is not equal to E. And order of x divides order of G. One among the theory which we have discussed. Order of an element divides order of a group. Okay. But order of G is 8 based on the given information. Therefore, order of x nothing but the divisors of 8. So order of x can be 2, 4, 8. Here 1 is also a divisor of 8, but order of x cannot be 1 since x is not equal to E. Suppose x is the identity element, then we can say that order of x equal to 1. In that case, 1 is the order of an element x. Okay. Right. So we need to verify this. Okay. The first condition, if order of x equal to 2, then fine, because that's what we need to prove. Order of A equal to 2, that's what here A equal to x, so this is done. But we have to check it. So this is done. But it is a question mark. What about others? What about 4? What about 8? Suppose if order of x equal to 4, what happened? Let's see. Then order of x squared. That means we are using order of hk equal to order of h into order of k divided by order of h intersection k. We are using this formula. So order of h into order of x into order of x divided by order of x intersection x. Like this, maybe you may remember, like this, we are having other formula also, order of x squared. The equivalent formula, that is order of x divided by GCD of GCD of 2 comma order of x. 2 nothing but the order of x. This is, so order of x equal to 4 and GCD of 2 comma 4, which is 4 by 2, which is 2. So in that case, order of x squared equal to 2. So take x squared equal to a, that implies order of a equal to 2 only. So order of a equal to 2 alone. Okay. So again, we are getting the same answer. Let us consider the third one. Suppose if order of x equal to 8, what happens? Then order of x power 4 equal to order of x divided by GCD of 4 comma order of x. Similarly, 8 by GCD of 4 comma 8, which is 2. Right? Again, you take x power 4 equal to a. In that case, we receive order of a equal to 2. In all cases, order of a equal to 2 alone. Order of k equal to 2 alone. Therefore, the statement is true. Right? Okay. Right. So there are several problems which can be used to solve based on this. So question number 5. If order of G equal to 63, then there exists A belongs to G such that order of A equal to 3. True or false? Verify. Right? Okay. Next concept is orbit and stabilizer. Suppose G is a group. Let G be a group of permutations of a set A. Of a set A. For each A belongs to A, orbit of a group, orbit of A for the group is nothing but collection of all sigma of A such that A belongs to G. A belongs to G. This O or B of A nothing but orbit of a group, orbit of an element A under the group G. Under the group G. Right? Like that, we can able to define stabilizer of A. So here, let G be a group of all permutations such that stabilizer of A under G equal to collection of all sigma belongs to G. Collection of all sigma belongs to G such that sigma A equal to A. Collection of all sigma A equal to A. The set of all stabilizer of A in G forms a group. That is, stabilizer of A under G form is a subgroup of G. Right? Okay. So by using these two concepts, we can able to derive a theorem, that is orbit stabilizer theorem. Orbit stabilizer theorem. Let G be a group of permutations of a set A, then for any A belongs to capital A, orbit of A under group G equal to index stabilizer and number of elements in a group G equal to product of orbit of A over G into stabilizer of A over G. Right? For example, we can check it. We can easily identify the stabilizer and orbit of an elements of a group. Suppose if we are taking an element of group with the order 8, then any group with 8 elements, we can easily find out and we can cross check also. Right? Okay. So up to now, we have discussed several concepts on start from Lagrange theorem, problems based on orbit, stabilizer, and what subgroups, mainly subgroups, and how to use the order of an element, order of a group, and solve this. Okay, right. So we need to know how to find the stabilizer and how to find the orbit. Right? Check any book, you will get plenty of problems on the topic. So next we are going to discuss about normal subgroups.